So in the literature and my PhD friends, I knew I was onto something when I made one of my favorite and smartest PhD friends slap the table and told me that I cannot challenge the fundamental laws of physics. The inverse square law is the inverse square law. It's a law. You can't change the law. And it's like, I'm not changing the law. We're just using the wrong terminology. It is absolutely true, but it's based on human perception, and like for our photography friends, it's key for designing systems and taking good photos, shooting good film. However, it's from a point source. So this is a candle. If we set it in the middle of the room and had a light meter and moved away from it, the numbers would be a logarithmic decay based on the distance from that point source. And the term PPFD is Photosynthetic Photon Flux Density. I always get nervous saying that one in person out loud. But technically, density is the amount of energy or mass in a three-dimensional space. What we have here is actually an aerial density. This is a two-dimensional plane that's being managed and monitored and designed to. So we are applying a two-dimensional measurement and specification to a three-dimensional system. That's problem number one. So right now, this is 26.1 watts per square foot. This is 700 micromoles going down to under 100, going from 1 to 10 feet. That follows the rule pretty well. It's not a perfect representation of the inverse square law, but it does track and it does correlate to what the law says. But the second line is 20 watts per square foot. And the rate of decay is completely different, and it doesn't taper off. And it's not flat, but it's much closer to flat. So how is that possible? Well, if we hang one light in the middle of a room or the middle of a space, you get closer to that logarithmic rate of decay. But we are designing systems. We're designing arrays. I mean, the basic ceiling of a grow room or a greenhouse is a very large two-dimensional space. So this is not apples to apples right out the gate. And I noticed this for the first time when double lenders first came to the market. I went into my first Gavita room, and I saw these 7-foot tall plants, and I climbed up on a ladder with a light meter, and I got up to the top, and it was only at 750 micromoles. I was like, well, that's weird. Like, it should be 1,000 here, but the lights were still 5 feet above the top of the canopy. And I did some measurements going down a distance, and I was like, well, that doesn't follow the rule. This was 2015, 2016, whenever Gavitas were starting to get commercially deployed. So that's when the hamster wheel started turning, and I lost a lot of sleep. So again, just looking at different wattage densities in a system, because we're not dealing with a point source, we're dealing with systems engineering at this point. You can see the 26.1 grams per watt. Watts per square foot does have the curve, but we can pretty much plateau that line by putting more light into a room and into a system by raising the lights. You know, it's non-traditional thinking. Everybody thinks you need to put a racking fixture 6 inches away from the canopy to get 1,200 micromoles to get your yield. The reality is, if we put enough light and enough energy into the room and into the system, the yield is based on the total rate of inputs, not on the level of a two-dimensional plane. So this was an earlier rendition. I did the other data set last night, but this is what, it shows this line plateaus at 1,000 micromoles. Obviously, you're going to run into canopy interference and shading, and everybody talks about penetration, which is I've got a fun YouTube video out there if anybody wants to watch it. When I was discussing this topic 2 years ago or 3 years ago, bored during the pandemic. But this means that we're flooding the space with light. And the physics of light are very strange. But this is not a point source of light. These fixtures are 6 or 7 feet from the canopy. This is a 200 light room with 100 and some varieties in it. And he's hitting his yield numbers and his quality numbers here. Even though if you put the light meter at the top of the canopy, it may be 800 or 900 micromoles, he's still getting his whatever his metric is. Everybody wants around 2.5 to 3 pounds of light. We're getting some guys getting up to 4 pounds per 600 to 800 watts now. So new heights are being reached on yield potential, but I am specifying top lights at a minimum of 5 feet away from the canopy and not trying to force the light on the top of the plant, because what happens, and you see it with high pressure sodium, you get a really dense flower at the top, and then you get a really loose larvae flower at the bottom. And one thing I noticed, again, when I first started running trials with LEDs, is that the uniformity of the quality of the flower from the top to the bottom of the plant is much more consistent than it's ever been with HPS. There's other reasons for that. Going back to that photo bleaching, again, that'll be next year's topic because of the heat that comes from a high pressure sodium lamp. But, having lights up out of the way, and the Dutch do this unintentionally, the greenhouse methodology, they always want to put fixtures 8 feet from the plants. And I always question that, but it makes sense. And I don't know if they've taken credit for it now, so I will. But being able to pull your numbers and keep your hardware out of your hair is key. So this is the difference. I mean, when we have a point source, even if it's in a system or an array in a room, we're going to look at 2,000 micromoles right under the light. It's going to decay down to this rate. If you go out in a cornfield with a tall ladder or in a greenhouse with a light meter, you're going to see 2,000 micromoles. So obviously the sun's a lot further away, the math adds up, there's still some decay on that total amount of energy, but the distance that we're looking at is negligible. There's no difference. And I was talking to a professor who was working on corn at Cornell, and he's like, how do I grow 15-foot tall corn plants indoors? I was like, you need to put your lights 15 feet above it and put a lot more energy in. It's going to be wholly inefficient. But for crop science, this is what you need to do. And he's like, you're absolutely right. No one here believes me. So I got at least one other convert. And in a greenhouse, you get a hybrid of these things where it gets more complicated. But this is where radiometrics and agronomics fall apart. So as far as the terminology and systems engineering, we're looking at this from an optimization standpoint. We're looking at efficiency. We're looking at reducing energy and getting the most output from your inputs. So I took this screenshot from a video. There's a lot going on right now in the science of the physics of light. If you guys want to enjoy some cannabis and sit and watch hours of good footage, Niles Berglund has a bunch of very high resolution mathematic demonstrations of how light works through different materials. And I actually there's the thinking that, and it's known that light has particle properties and wave properties, but the wave properties are what are most applicable and we're finding it to be most true. And when you get waves, you get things that act like a physical thing, like water. So basically this is light moving through a drop of water, and you can see it's condensing, and then you'll get interference, and it'll bounce back through and get re-angled. And another thing that we're doing when we're running LED rooms is we're running the humidity much higher than we would in HPS rooms. So there's another physical interface that we haven't really looked at yet, is the physical interface between water and light and water suspended in the atmosphere. So you get this diffusion, diffraction, and refraction of light so that it almost acts like a gas. Obviously there's the direct incidence, but we need to look at light on a much smaller level, itty bitty level, and this is what they're doing with modeling. And in plants, there's also some unique characteristics with chlorophyll and transmission through the leaves. But our understanding of light is going to improve because of our understanding of light in plants. And another case in point, this is using a penny, but you could also have a leaf. Light will actually move around and reconvene behind something that it runs into. And I thought this comic was kind of funny. Can your stream of particles do that? So wave theory, light theory, and physics is, again, where I'm starting to spend a lot more of my time. So this is an image. It looks like the Northern Lights. Anybody know what this is? Light pollution from a greenhouse light. This is across the Michigan River. Got it, Zach. So this is a mix of LED and HPS light diffusing out of the top of greenhouses. And the reason we can see it from a distance is because the water in the air, that cloud, is actually redirecting the light to come to our eyes. So this makes the point that humidity and moisture in the air actually change the light physics and how it moves around in a room or in the system in the environment. So that's another thing that in the literature has not really been considered much. So while we're designing systems, especially for vertical farming, everybody's looking to optimize efficiency. If you're growing lettuce under a sole source lighting in a warehouse, everybody's bean counting. Every input counts. I mean, it costs money and fuel to run these things. So we are still designing on a two-dimensional plane when we actually have a three-dimensional consideration of canopy, depth of canopy, crop interference, shading, diffraction, refraction, and then also some unique activity, the way chlorophyll actually opens up and lets more light through once it's saturated. And this is an old image from one of my heroes, Dr. Bruce Bugbee, and this was from the 80s, where he was talking about, and it was fun actually, in Morocco, I had a physicist call me out and say these numbers were BS, and that's actually true. Did you have a question?
No, 5 minutes.
5 minutes, okay, cool. But the point remains, it takes X number of photons to create X number of carbohydrates to create X number of grams of biomass. What angle those come from, how they're delivered, how they're received, how they're captured and converted is what we really need to be looking at. Yeah, 1988, he was way ahead of the game, and he still is. But we need to rethink the way that we design light systems, controlled environmental agriculture, and efficiencies as a result. So this is another tie-in because light and sound are very closely related, actually. And I stood on a stage in 2017 in front of a room of horticultural lighting professionals and gave this concept, and I got crickets. But there's starting to be more and more validity to this. Plants perceive light like we perceive sound. So we look at major and minor tonalities. You know, there's slight shifts in sound that make us perceive our mood changes when we hear a minor note versus a major note, or you add a 12th or 13th, you get jazzy. And like plants react to light like humans react to music. And again, one late night on YouTube, this thing came up. I was listening to the math of music theory, and these numbers came up, and it's 440, 660, and 733. And in the lighting world, that's blue, that's red, and that's far red. In the music world, that's Baba Black Sheep in A. Hertz and nanometers aren't the same, but I thought that the tie-in on the numbers and the overlap was pretty profound. And anyway, the story goes on. So I do want to thank all the people that have inspired me to get to this point. Bruce Bugbee, I mentioned, Dr. Van Ertzel, who actually just recently passed away. Actually, on the day that I got to speak at the conference he was supposed to be speaking at. Eric Matos, Ryan Hunt, and a good friend and now colleague, Christopher Sloper. So that's it. Any questions? Right on time.